Hi, welcome everybody to the AIAB Annual Conference 2021. The power of I in BIM combined with the power of the cloud is what we're going to look at today. My name is Stephan GUMPERT and I'm a Senior Technical Specialist covering both structures, fabrication, cloud and automation. Let's look at the basic agenda. Overview first, followed by the challenges in design and fabrication. Next, we're going to have a look at what BIM has to offer, especially in particularly in the I component of BIM, followed by looking at BIM 360, which I believe is the cloud platform of choice for BIM. Again, focusing on that I component. And then with data, ultimately being that new commodity or the commodity of choice, making sure that that's accessible anytime and anywhere. And the presentation wouldn't be a presentation without a call to action. So from an overview perspective, we're going to cover three different industries. We're going to cover the structural industry, both steel and concrete, while considering the fabrication, and also having a look at the MEP side of things. Again, focusing on design and the fabrication, maybe not so much the E for electrical, but definitely the M and the P. If we start with the challenges and trends in design and fabrication. So with structural, there is quite a few challenges. Lack of early engagement, the lack of considering what it costs to fabricate something and to install something is impacting the cost of projects. Small amount of coordination is challenging projects. Lack of material management and optimization of designs is all impacting the way things get installed, ultimately ending up with, I guess, poorer design decisions. We have inaccurate bids because of the lack of information. We end up with wastage of material, which costs back charges and costs the project ultimately, with ending up with a lack of coordination of the trades. If we look at the MEP side of things, it's very, very similar. The design and contracting workflows are disconnected, meaning that the two different groups are working siloed, ending up with costly variations and RFIs out on site, where things aren't where they originally intended to be, because of the poor coordination of these groups of people. And with projects being expected to be fast-tracked with unrealistic delivery expectations, all these is impacting these challenges even more. If we look at fabrication, again, same sort of process as the MEP space, that the workflows are disconnected. Quite often, when you get to the fabrication space, things are built from scratch, which again is challenging and is a problem because it's time consuming. Developing new skills in that fabrication space, minimizing waste in fabrication, labor shortages out on site. These are all challenges that exist in the fabrication space today. The good news is digital collaboration is at an all-time high. More and more people are working collaboratively together, not on all the projects today, but only some of the projects. Governments are mandating BIM on projects as well. So more and more areas around the world are mandating that BIM must be used on projects to deliver them. And technology is becoming more and more popular through these projects, robots, AI, cloud products, laser scanning, you name it. There's a whole range of these products that are entering the space today, which is making our life easier. And of course, lastly, the introduction of manufacturing processes, ultimately ending up in industrialized construction. So modularizing your installation of your components as opposed to piecemeal installing or cutting things out on site. But the only way that this will actually successfully work is if the design and analysis space work together with the design and documentation space, and ultimately work together with the detailing and fabrication space. all three facets or all three rings of information need to intertwine and work together. If we look at traditional means of working in this space, you'll see that each of the different disciplines technically hand over a static 2D document of some sort to the next phase of the project. And this is that non-BIM based workflow. What we really want to do is information that we generate during the design phase should be shared with estimating. It should be shared, the estimator should share that information with the fabrication space and so on and so forth. So ultimately what we want to work with is we want to work with those BIM-based integrated workflows so that information flows uphill and downhill throughout the project. What we end up with is we end up with a dynamic environment in which we can collaborate across design and detailing. When we share the information through to fabrication, we reduce the potential for errors inside fabrication. And of course, if we share that information out to site, the installation of all these components becomes a whole lot more effective. So let's look at some examples of BIM in that design space. First, let's have a look at the structural side of things. We can model our components, our steel components, our concrete components in Revit, for example. We can then, using that I component of the model, share that information to robot structural analysis, sit down, do our code checking, potentially change those steel sizes, and then update that model in the original Revit side of things to be able to end up with that good system of sharing that I component from one phase to the next without having to create one model in Revit, one model in robot structural analysis, and work independent of each other. If we look at the HVAC analysis side, with Revit, for example, we define spaces, zones. These zones have volumes. Those volumes are used to analyze heating and cooling loads. We can then generate our systems for heating and cooling with our inlets and our outlets, where our equipment is, where the air comes out, the volume that comes out, and ultimately be able to perform the analysis in Insight, each time utilizing that I component from one phase to the next all the way through. If we look at Revit from a piping design perspective, being able to lay out where those pipes are going to sit, what size those pipes are going to be, analyze the systems for, flow rates, whatever it is that they're required to be analyzed for, then be able to generate reports and schedules from those models, ultimately, again, is utilizing that information a whole lot more. One of those components that were previously shown in that diagram was estimation. You can see here in this case, in Revit, we have the ability to take that design component of the ducting or piping, for example, for that matter of fact, convert them to fabrication parts, take those fabrication parts through sharing that I component in that Revit model over to the fabrication suite of tools, and using SMEP to then use the information for material costs, fabrication costs, and installation costs which exist in the databases in SMEP to then ultimately be able to provide a good, clean bill of materials or bill of quantities for that end project. But the I component we're talking about comes in many different forms. So let's have a look at some of those. If we look at it from a structural perspective, you can see here in this case, we know what the material grade of the component is. We know what the paint area is, what the cut length, what the weight, the exact weight, and so on. All these things is information that somebody else could utilize downstream or even in the current space of the design process. Let's look at a piece of equipment. So here you can see an air conditioner. This air conditioner doesn't just have a physical space or an appearance. It has inlets, outlets. It has information on, flow rates, pressure drops, sitting all as part of this component, which can be used in different facets of the design for the project. The important part is that data doesn't always exist in physical analytical data, right? It's also graphical, right? So you can see here, knowing what something looks like from a rendered perspective, or even knowing what it's looking like in a shaded mode just while looking at the model is super important, because let's face it, we've all heard this quote before, a picture tells 1,000 words. And this is really important. The data is so important. So whether it's space data, flow data, piping data, all this information is super, super important. The problem is, what do we do with this design, with this information during the design of a project? What actually happens? Well, ultimately nothing, because what happens is we finish the project, we hand over our 2D deliverable, and this information gets stored and virtually never used. All this very important data could be used elsewhere on the project. Something to consider. If we quickly have a look at BIM in fabrication, there's lots of clear examples, but the common example that I always show is the export and synchronization of that Revit model to advanced steel via the SMLX file. I spruik this method all the time because realistically, it is actually a really, really good workflow. Creating that design model in Revit, sharing it with advanced steel, producing those deliverables for assembly drawings, part drawings, NC files, DXF files, and so on. This is super, super, super important. And it can save a project a lot of time and a lot of money rather than building two separate siloed models. This is really, really valuable. If we look at the BIM 360 side of things, my strong belief here is that BIM 360 is the best complement towards BIM, or it's the cloud platform of choice for BIM for sure. Yes, there's a visual component to this data. It is also a file repository, so you do have the ability to store files in there. You can see in this particular case, I've got files in there. And ultimately, one of the big parts that makes this system so good is that the files that you store in here are also viewable. At the moment, BIM 360 supports around 70 different file formats, meaning that when you click on a file and you open it, in this case, I've opened up a Revit file, not only can I see the 2D drawings that are produced as that static 2D deliverable, but you're also able to see the 3D model, the components that are in that model. And when you click on those components, you can see the data that you saw in the design space. This is the I component of those BIM models, but in the cloud, right? If we go back and have a look at that previous example of that structural column, you can see here I've uploaded the same model into BIM 360. When I view it, I can see the same component. There's my paint data, my cut length, my weight, my material grade, right? So the information can be seamlessly shared from one place to the next by this cloud. Now, the important part to take away here is that this data is accessible anytime, anywhere, right? Whether I'm using a tablet, whether I'm using a PC, whether I'm using a phone, all this information is accessible anytime, anywhere. In fact, it's a zero install. So if you go onto the PC itself, you're literally just going into a Chrome browser. On the tablet and phone, of course, we will go to the App Store, download an app, use that app, and it doesn't matter whether it's Android or iOS, both platforms access the same projects the same way, being able to utilize that I component to the nth degree, no matter whether you're in design, fabrication, or construction. Let's have a look at this, an example of how combining the power of the cloud together with design is actually making the flow a whole lot more efficient. Now, keep in mind, this is just one example, but good example nevertheless.
There are more globally distributed projects. Efficient collaboration, communication, and seamless data exchange between teams are critical. It is also common for structural engineers to enter the same data into several different software applications multiple times for different purposes. With each iteration, several different models are produced, making it hard to collaborate between structural designers and engineers. This poor collaboration process is prone to errors and impacts the quality of the project. A solution for all these challenges can be work sharing and using the extended BIM workflows across the design process. Rather than working in siloed systems, structural designers and engineers can use the BIM 360 environment. BIM 360 Docs integrates the entire project workflow from design to construction across one common data platform. The extended team of structural engineers can easily review what has been done in Revit and stay up to date on the current structural project. When project teams have the right information at the right time, work happens faster. BIM 360 Docs lets them publish, manage, review, and approve all drawings, documents, and models, anytime, anywhere. The project teams can not only review all information, but they can also download project files. Having access to the project data, a structural engineer continues the design process, performing structural analysis and running code checking optimization. The Revit analytical model can be sent to Robot Structural Analysis Professional with all the information needed for structural analysis, including boundary conditions and loads. Interoperability with Revit, combined with powerful analysis and code checking engines, gives engineers the best tools and fastest path to train up staff. Thanks to many ways of presenting results of the analysis and the ease of accessing them, structural engineers can very quickly prepare the final documentation for review and input by project stakeholders. Results can be presented in the form of colorful maps of displacements, moments, stresses, etc., obtained during structure analysis to provide a visual snapshot of how the structure behaves. All of these make the software very intuitive and easy to use. Once designs change, and analysis has been completed by the engineer, the information can be brought back into BIM 360 Docs to allow the designer to review the design changes and update the physical model accordingly. Here, structural engineers can upload their structural analysis and code checking documentation in the PDF file format. Also, analysis results can be easily stored and explored in the Revit environment, so Revit users could gain knowledge on structures' behavior, have insight in consolidated detailed results, take appropriate design decisions as well, and even properly document these. Once the Revit model has been updated after the analysis and code checking process, the structural engineer can upload a new version of the Revit project to BIM 360 Docs. Then the structural designer has access to the updated, optimized model by the structural engineer via BIM 360 Docs. Using the Compare tool, the structural designer can get insight into what has been changed in the model. BIM 360 has integrated change visualization that lets users compare the changes between two selected versions of the project. This summary provides a quick accounting of changes made by the structural engineer during the code checking process.
So you can see the power here that we're referring to, right? The visual data, the analytical data, you can see here that it's changed from an IP 240 to a 270. This sort of information is normally difficult to record and manage. Ultimately, you can see having the data flow across all the systems means that everyone can utilize the same information easily, quickly, and ultimately providing a more efficient workflow in your project. But remember, that was just one focus. We could do the same thing for fabrication, for construction, have that data flow on. Ultimately, wanting to get away from that static 2D deliverable. And look, you may still have to deliver that static 2D deliverable from the legal requirement. But what we're trying to do is get you to change the way and ultimately end up sharing that information upstream or downstream, depending on where you are in that design process. Ultimately, the call to action here is, how can you change? How can you influence the change and delivery in that project to improve the design, fabrication, and construction of that project? You may believe in the power of doing this, but somebody else may not. So how can you influence that project and make it different to ultimately end up changing the way you execute on projects? Thank you.
Thank you, Stephen. It's Q&A session now. If you have any questions, submit them in a Q&A box at your right panel. Stephan is here to address your questions. All right, Stephan, we have already received a number of questions. So the first question is from Toby Chan. She asked that what has been a recent example of where the transfer of data from design to fabrication occurred? Can you please answer?
Sure, it's a good question. So recently I had a plumbing customer or company come to me who were wanting to change the way they do their plumbing assemblies out on site. So rather than developing their plumbing assemblies out on site, cutting material out on site, this customer was looking to take the design, turn them into as-built fabrication assemblies inside the design space, build the assemblies in the workshop, and then transport these assemblies out to site, which meant that the pre-lay was much more efficient out on site.
Cool. And the second question is from Peter Zhang. He asked that as I'm a steel fabricator, what Autodesk BIM software he should adopt?
That's an easy question. That's one of my pet favorites, actually. So Advanced Steel is the fabrication software that Autodesk provides. The benefit of this software is very obvious in my presentation here, in that it can be linked bidirectionally with the design of Revit model straight to fabrication. So Advanced Steel is something that you should then explore.
Mm-hmm. And Liz would like to know that, Stephan, can you tell us what the impact or power of early engagement of the downstream process are in a project?
Good question, good question. So, I mean, if you can get those disciplines engaging in the design process early on, and we're talking about the downstream processes, fabrication, site works, they can then potentially pick potential problems in the installation, in the fabrication, maybe in the delivery of those design components to site, and obviously fixing things, making changes in the design to suit some of these potential problems is much easier to do in a digital form than to try and fix those problems out on site later on.
Mm-hmm. And the last question is from Timothy Tong. He asked that what has been one of the most impactful examples that you talk about in design today?
Definitely. So actually the interesting part here is that I had a construction customer in Perth in Western Australia, actually, who was very much a traditional construction company. However, they changed their processes and started adopting the BIM models that they were receiving from the architect, from the engineer. And there was 2 or 3 individuals out on site who would prepare special views for that set of work for that week and then publish those views to BIM 360. Now, what this made this really impactful in this case is that to make the people adopt this technology out on site, because obviously it's very traditional practice, to build change, they actually threw away the printer on site so that nobody could print a drawing. And so they were still able to access their 2D drawings directly from the tablet, but these views that the construction manager on site built for the people doing the work that week gave them a much bigger and better view. And let's face it, a picture tells 1,000 words.
Mm-hmm. That's truly insightful. And thank you so much for sharing today, Stephan. Thank you. See you again soon.